Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we solved one numerical problem on the bending moment and shear force calculation and their diagrams. Now, another numerical problem we will be taking today, that is the problem says that determine the axial force, the shear force and the bending moment acting at any section theta in the circular arc AB. So, AB is a circular arc, okay, as shown in this figure. Okay. So, at the end B you are applying one vertical force P, okay. Due to that action of externally applied force P, you have to calculate some bending moment, shear force and axial force at any section theta, okay, as shown here. So, O is a point, this point actually, okay. You can consider that is the center of the arc, circular arc, okay. So, what is my first job? If we want to solve this problem, what is my first job? First job is to draw the free body diagram. So, let us draw the free body diagram. So, we will remove this support, okay, and we will replace this support by applying the forces, okay. So, y direction force, x direction force and moment, because okay. So, you can have this is a y and this is x, okay. So, these are the support reactions, because that support was fixed support. So, therefore, we will get all the three components of reaction, okay, fine. So, this is the free body diagram of that particular say circular arc, and as per the geometry actually. So, if I consider one section here, so this is my one section, section 1 okay. So, this angle is theta. So, therefore, this is r cos theta, okay. From the geometry I can get it, okay. So, if I draw, now this is the free end basically this is a kind of cantilever thing, right. This is the free end, okay. There is no support here, the support is here only. So, it is always convenient for any kind of cantilever structure, it is always convenient to come from the free end, okay. So, we will be coming also from the free end. So, let us take the right hand side of the section 1 and draw the free body diagram of that. So, this is my section 1 okay, and this is P sin theta and this is P cos theta, component of P, okay, because this is r cos theta as shown here, okay. This is your section 1, this angle is theta, okay, and you are getting the development of your shear force like this and bending moment like this and the axial force like this, okay, fine. In this case actually your load is not only in the, your structure, loading and all those things are not exactly in the xy plane. So, therefore, it is in the xy plane, that is okay, but the thing is that it is not, you do not have the situation is not like that you are not having the axial force, okay. The earlier cases whatever you have seen that you did not have the axial force because the x direction force was not there, but here the case is not like that, you will be getting the axial force also, we will see that. So therefore, the section will be associated with the shear force, bending moment as well as the axial force. Okay. As we discussed that in xy plane, if you have the loading, you will be having all three components internal forces, right, internal forces, two internal forces and one internal moment, okay, the bending moment. Okay, fine. So now if you try to resolve, the first one is that if you try to consider the equation of equilibrium for F tangential direction is 0. Okay. So, whenever it is not mandatory that all the times you will be considering the equilibrium. Equilibrium means it will be valid for any direction, right. So, I am considering the summation of all forces in the tangential direction is 0. I can do that. So, what are the forces that are acting in the tangential direction? If you look at this figure, this F, that is the axial force, as well as this P cos theta, right. So, F plus P cos theta is equal to 0. Okay. So, these are the forces acting in the tangential direction. Okay. So, from this I can get the axial force F equal to minus P cos theta. Minus sign tells that whatever direction we considered for F is not correct. Okay. Fine. Okay. Then I am considering F, summation of F in radial direction is 0. Summation of all the forces in radial direction is 0. So, now what are the forces are acting in the radial direction? This V, of course, this is in the radial direction, that is the shear force, and this component of P, that is P sin theta, is also acting in the radial direction. So, therefore, I can simply write V minus P sin theta is equal to 0, from which I can get V equal to P sin theta. Okay. Fine. Any issue? I hope it is okay, right. Okay. So, now if we consider the moment equilibrium, now we are going to consider the moment equilibrium. That is summation of moment with respect to section 1 is 0. So, there the moment MB is acting fine. So, clockwise moment I am considering negative as per our sign convention, and then this P I am not considering the components, rather this P into R cos theta, okay, will give you the clockwise moment. So, minus MB minus PR cos theta is equal to 0. So, from this I can get MB equal to PR cos theta. So, you have got the shear force, axial force as well as bending moment at any particular section which is making an angle theta with the x axis. Fine. So, with this I conclude your bending moment and shear force chapter. I hope that you have understood the concept. This is basically the new concept you are getting, because bending moment and shear force and this is nothing but the backbone of the analysis or things of your mechanics of solid, I mean for any slender member, right. So, we will see that later on when you will be finding out the deflection of the slender member, when you will be finding out the stresses developed in the slender member. So, for all the cases you need to obtain the bending moment and shear force at any particular location or particular section. Okay. So, with this I conclude. Now, we will be moving to the next chapter, that is torsion of circular shafts and thin walled tubes. Okay. Fine. Okay. So, now we are going to talk about the torsion of circular shafts and thin walled tubes. So, as I told you in the very first class that we are not going to talk about the torsion in the rectangular shaft, because that is beyond the scope of this particular course. So, now if you consider this kind of say circular shaft, okay. So, for the time being we are considering the solid shaft, and this shaft is basically under the action of the torsional moment mt. Okay. The circular shaft loaded only by twisting moment mt at its ends, okay. At both ends you are having mt, that means you are having a circular shaft, you are giving the twisting moment like that, okay. And the equilibrium requires that each cross section of the shaft, okay, must transmit the twisting moment mt, is not it? Because if you consider two parts, this is another one part and this is another part say, and you are cutting at say this plane you are cutting, okay, this shaft, and you are separating out these two parts, this is part 1 say and this is part 2. You will see that to satisfy your equilibrium, here if you have the empty, you should have empty here also, and you should have here also and here also, right. So, that means at the equilibrium requires that each cross section, okay, of the shaft must transmit the twisting moment mt, that you have got it. Okay. Now, we are going to talk about the symmetry argument. Now, what is that? Now, basically if you look at, if you consider one particular cross section, okay, say this is one cross section, some I am taking some slices, okay. So, I have the complete shaft, I am taking some slices of say depth delta z, okay, and there we are considering that the originally straight radius OA before application of the twisting moment, the OA was the original radius, okay. Now, this OA is taking the shape of some curved surface OA prime after giving the twist, okay. What did I say? OA was the original radius before application of the twisting moment. Now, after the application of the twisting moment, that OA takes the shape of some curved surface or curved line, that is OA prime. And because this is a kind of say isotropic material, so I mean there is no reason that you will be getting the different configuration for different radius. So, if OA is experiencing the twisting moment and getting the shape of OA prime, right. So, therefore, OF another radius on the same plane will be taking the shape of OA prime and so on, the curved shape. So, the initial straight radius is becoming the curved lines, okay, after application of the twisting moment, right. Now, suppose that one end of the slice, okay. Now, suppose the one end of the slice, so this is the thing, okay. Now, one end of the slice is getting bulged out, okay, after the due to the application of the twist. Let's say, I mean suppose, I do not know what kind of shape it will take, just we are assuming that after the application of the twist or the torsional moment, that this surface is getting bulged out. So, therefore, to satisfy the equilibrium condition, the lower part also should bulge out, is not it? It will also should bulge out, or suppose it is not bulging out, rather it is getting dished in, okay. Some kind of depression you are getting. You may get the bulging out or dished in situation or the configuration. I do not know which configuration it will take, I am just assuming. I am assuming that after the application of twisting moment, it might take this kind of shape like your muffin, okay, or it might take this kind of shape where you are getting the depression like that. Now, if you consider the another segment of the shaft, that will also will be having the bulging out or some depression like that. Now, do you think, now basically this is a continuous shaft, right, and when you are applying some twisting moment, do you consider that segments are getting separated out? No, that is a continuous slender member, that is a continuous circular shaft. Okay. So, if the upper part is getting bulged out, the lower part will be also getting bulged out. So, this part and this part will never match together, right. So, it will be impossible to fit a number of such deformed slices together to form a continuous shaft. So, this part and this part will not fit at all, even this part, this destined or the depressed part will not be fitting to this part also, am I right. So, if you get this kind of configuration after deformation, after the application of the twisting moment, then basically your geometric compatibility is not getting satisfied. So, to satisfy this, we can conclude that when a circular shaft is twisted, its cross section must remain plane. So, what we can conclude? We can conclude that based on this discussion, we conclude that when a circular shaft is twisted, okay, its cross section must remain plane. So, this kind of bulging out or destined configuration is not acceptable, they are ruled out. So, only the plane section will be remaining plane even after the application of the twist. Okay. So, that is the first conclusion we are drawing from the symmetry argument. Okay. So, now what we can say, because we still do not know that how the configuration or how the deformation will take place, okay, how the configuration of or the deformed shape will be there. Okay. So, that we can find out from this figure. Say in this figure we have, before the application of the twisting moment, we have this plane H O A B C J. So, this is the plane. Okay. Can you visualize the plane? So, before deformation I am considering one plane, okay, in this segment, okay, under the action of this twisting moment. Now, after application of the twisting moment, this plane is taking the shape H prime O A prime B prime C J prime. Okay. So, after application of the twist, let us say it is taking the shape like that. I mean from our bare eye or without any say discussion, we can think of like that. Now, if the curvature or this line, so what is the shape of B prime C J? So, this is the shape of B prime C J line, C J prime line. So, this is the shape of B prime C J prime line at the bottom surface. Now, just below that you are having another segment you can consider like this, which will be behaving very similar to this segment, right. If it behaves very similar to this segment, then of course, on the top surface, this is your the top surface, on the top surface you will be getting this kind of deformed shape, A1 prime, O1, H1 prime, A1 prime, O1, H1 prime, right. And this top surface will be connected or will be touching the bottom surface of this segment, the upper segment. Now, if their radius or the rotation of the radius is such that it makes B prime C J prime line in the upper part, and the lower part it makes A1 prime, O1 and H1 prime, are they matching? This is the first question. They will never match, right. So, they will never match, isn't it? This line, the line on the bottom surface is not matching with the line on the top surface of the next segment. So, therefore, this is not matching at all. So, therefore, there is some ambiguity which has to be resolved. Okay. Now, if you look at, if you consider okay, that B prime C J prime is not taking that kind of curvature, it is taking this kind of curvature. Okay. Now, if it makes this kind of curvature, so then that will match with the lower part, fine. But now, if I rotate, this is my x axis, x axis here. If I rotate 180 degree, if I give the rotation 180 degree, so this B prime C J prime will be coming at the top, fine, and this A prime O H prime will be going at the bottom, because I am just rotating the drum. So, this is the drum, this is the segment, say I am just giving the rotation like that. So, top surface is becoming the bottom surface and bottom surface is becoming the top surface. I can do that, I am doing that. Okay. So, after that you just look at what I have done. I have not done anything, everything is remaining same. This segment is under the twisting moment empty and everything is remaining same, the sense of rotation is remaining same. Only thing is that under the same loading I am just rotating the whole drum. Okay. I am making the top surface as the bottom surface and bottom surface as the top surface, that is all. But by making that, what I am getting, before rotation you are having this kind of say deformed surface, okay, on the top surface or deformed line on the top surface. But after rotation you are getting this kind of deformed line on the top surface, they are not matching at all, right, they are not matching. So, from the symmetry argument we can say that the curved lines, okay, due to the application of the twisting moment, the straight radius will be remaining straight, they cannot be the curved radius, because curved lines are not satisfying the symmetry argument. Agreed? So, what we can conclude? We can conclude that the diametral lines, that is my second conclusion, diametral lines deform into curved lines is ruled out, okay, by symmetry. The straight diameters are carried into straight diameter by twisting deformation. Okay. So, these two statements are very important, which are coming out from the symmetry argument. First conclusion is that when a circular shaft is twisted, its cross section must remain plane. So, cross section, if it is circular, it will be remaining circular and remaining plane. Okay. It will not be bulging out or dished in. Okay. And diameter lines deform into curved lines is ruled out from the symmetry argument, already we have discussed. So, therefore, the straight diameter are carried into straight diameter by twisting deformation. So, straight diameter will be remaining straight even after application of the twisting moment or the twisting deformation. Okay. So, I will stop here today. So, in the next lecture we will be discussing about the stresses developed due to this, or stresses as well as strain developed due to this application of twisting moment. Okay. So, thank you very much.